Hello, everyone. This is Math 6, Day 3. I apologize for the infinite screens. Hopefully, everything's up and running. So, today we're going to be looking at lesson 15, 16, and 17. Again, we'll do the practice set problems and go over them in class. This is just the new concepts and the introductory examples that we're going to go over by video. Here we All right, so in lesson 15, problems about equal groups. And you're welcome to read through all of this or go back through. This is again on page 78. We're looking at lesson 15. A reminder how the book kind of breaks it down up here. You'll have the number of the lesson and then the different concept or concepts, maybe 2, 3 on some days that it's going to go over. And then there'll be at least one example, sometimes 3, 4, 5 examples. We won't go through all of them, but they will be there. So when we're talking about equal groups, again, anytime we see a bold or highlighted word, that's a new term or something worth writing down or making a note of as we go through, just because there's a lot of terminology, a lot of vocabulary that we go through throughout the course of a textbook or an entire year in math. So in this equal group problem, it says in the auditorium, there were 15 rows of chairs with 20 chairs in each row. Altogether, there were 300 chairs in the auditorium. So that's saying 15 times 20 equals 300. So if we know the number of groups, the number within each group, we can find the total. And as long as we have 2 of the 3 parts of information that we need, we can find the other. So if we're given the number in a group and the total, we can figure out the number of groups. So if we're given number of groups and the total, we can find the number in a group. As long as we have 2 of the 3. If we're only given 1, we need more information. So number of groups times the number within the group is going to equal the total. And depending on what we're starting with, we're going to use our inverse operations. We're multiplying in this case, so we're going to be dividing in order to find our unknown or what we're looking for. Okay, the example here says at Russell Middle School, there were 232 7th grade students in 8 classrooms. If there were the same number of students in each classroom, how many students would be in each 7th grade classroom? Okay, so we know the total number of students. (232). You can see both. Okay, so there's 232 in the 8th grade classroom. There's the same number of students in each classroom. There's 8 classrooms, right? We want to know the number of students in the group. So number of classes, which is 8, times the students in each class, which we'll just call S for students, even though it looks like a 5. And that equals 232. So since we're multiplying, we need to divide. We divide both sides by 8 in order to get the number of students. So we're left with 8 over 8, which is cancels out to be 1, and then 232 divided by 8, which comes out to be 29. And so we have 29 students in each classroom. Again, it has to be a whole number. It wouldn't really make sense if we said, oh, well, each class has 29.3 students or 10 and a half or something like that. Since we're talking about people in this example, we need to end up with a whole number. If we didn't, which is possible, then we would have to allocate different numbers to different classrooms. But since this one, it works out to be a nice even whole number, then we're good to go. So 29 students in each class. And then we could again plug that back into our original problem and say, well, 29 times 8 needs to equal 232, which it does. So we can check our work pretty quickly to make sure that we did it correctly. The practice set problem, we'll go over those on when we meet again, so don't worry about those. That'll be something we do in class. Okay, now lesson 16, and flip over there to page 82. Okay, we're looking at rounding whole numbers and estimating. So again, rounding whole numbers. We want to round. When we're told to, we don't just round because we feel like it or it makes life easier. We have to be told in the problem to round, and then the same thing with the estimating. We use rounding to help us estimate when we're given big word problems or trying to find to the nearest, whatever it is that we're buying supplies for a building project and we have to buy so many 2x4s that are sold in 8-foot increments. We would need to probably round and then estimate up to make sure that we have enough. So, okay, rounding, pretty simply, we're rounding to the nearest number. And sometimes if we have decimals or fractions, we can round it to the nearest ones place, we can round to the nearest tens place, or the hundred. So depending on how big or small the number, that'll probably affect what we're rounding to. If we're given a really small fraction or a decimal number and we're asked to round to the nearest 10 millionth, that doesn't really do us any good. We may be rounding to the nearest tenth or hundredth or thousandth or some sort of fraction, the nearest half or something like that, or the nearest whole number. So in this one, we probably want to round, since it's in increments of 10, we probably want to round to the nearest tens place. So we're going to look at the tens place. Okay, whatever we're rounding to, we look at that place value, and then we look at the value directly to the right. And then if it's 5, 6, 7, 8, or 9, we round up. If it's 4, 3, 2, 1, or 0, then we round down. So in this case, 7 is 5 or greater, so we're going to round our tens place up from 6 to 7, and that's going to give us 670. We can look pretty simply at a number line to see that it is closer to 670 than it is to 660. Now 5 lands right in the middle, but 5 we always round up. So remember 5, 6, 7, 8, 9, we're rounding up. 4, 3, 2, 1, or 0, we are rounding down. Okay, here we're not just told to round it, we're told to round to the nearest thousand place. So again, we have our ones place, 10, 100, thousands place right here. So we're going to look to the value directly to the right. And it doesn't matter what comes after that. It could be 8, 9, 4, 3, big, small numbers. It doesn't matter what comes after that. We're just looking at the value to the right. So it's a 7, which again means we're going to round this 6 in the thousands place up to 7. So the nearest thousand would be 7,000. Okay, so that tells us whether we're rounding up or down. Same thing if we're looking at a decimal number far to the right of a decimal, or whatever it is, we're looking at that value and then the number directly to the right. Not 2, 3, 4 to the right. That doesn't matter. It's just the value directly to the right. And then whatever digit it is going to tell us whether we're rounding up or down. Okay, now skipping ahead, when we estimate, make sure we're still recording. Sorry, it kicked me out earlier. I want to make sure it gets fully recorded. So when we estimate, that can help us answer problems. Again, we're only going to estimate when we're told estimate or round. We don't just, we're not given a big long problem and say, oh, I'm just going to estimate because it is quicker. It usually is, but we only do it when we're told to do so. So let's say we're estimating the sum of these two numbers. Again, sum means that we're adding. We have 467 and 312. Since both of these go out to the hundreds place, I'm going to round to the nearest 100. So I look to the tens place because it's right of the 100 place. And in this case, it's a 6. I'm going to round this up to 500. 312. Oh, I look to the value to the right of the hundreds place, and it's a 1, which tells me I round down. Sum means addition, so I'm going to call this 500 plus 300, and that's going to give us 800. Okay, not exactly the same as what this sum would be, but it's going to be close. So we first round, and then that helps us when we're estimating. Okay. And then we'll look at this practice set. If you want to do some of the other examples and look through them, go ahead. We will go over this practice set when we meet in class next. And then also we are looking at lesson 17, which deals with fractions and mixed numbers and the number line. So we just talked about the number line, 0, 1, 2, 3, 4, and then its opposite, 0, -1, -2, -3, -4, and continuing on. So we also have, besides integers, we can plot really any number, irrational numbers, we can plot mixed numbers, whole numbers, counting numbers, any of our numbers we can plot on there, except for imaginary numbers, which we won't even get into for several years. But we have mixed numbers where we have a number and a fraction. So that's what a mixed number is. So we have 0, 1, 2, 3, but just because that's where normally our tick marks are, doesn't mean those are the only numbers on there. Really, there's infinite numbers between each of these tick marks, between 0 and 1, 1 and 2, 2 and 3. So we can really plot anything that we want in between there. So if we have 0 and 1, well, halfway between 0 and 1 is 1/2. Between 1 and 2 is 1 and 1/2. 2 and 3 is 2 1/2. And then obviously the opposites, negative versions of those numbers, -1, -1.5, -2.5, and so on. So we don't just have to use halves or fourths or thirds or anything like that. We can have any fraction in there. So 17 and 17/18 or something like that. We can have any number that we want. It's just a number and a fraction, and we call that a mixed number. So if we're looking at example 1 here, point A represents what mixed number? So we know 1, 2, so it's going to be 2 and something because it's between 2 and 3. And then to know what fraction we're looking at, we count the tick marks. 1, 2, 3, 4, and then 5 would get us to the next integer. So we're 1, 2, 3 of our 5. So we're going to call that 2 and 3/5. Because there's 1, 2, 3, 4, 5 spaces between our integers. So that tells us what fraction we're working with. Up here, there was 2 spaces, so we're talking about halves. And so 2 and 3/5 would be the mixed number that we're looking at. And again, how we write mixed numbers, we do the whole number larger and kind of in the middle of our fraction bar right there, just so we know that that's our whole number. If we get too small and put it up here or down here, we can think maybe it's 23/5, which is not correct, or 3/25 if we think the 2's down here, which is incorrect also. So just make a point to make that larger and then your fraction smaller, just so you know what the number is that you're referencing. And then you'll see a lot of those tick marks on rulers or tape measures and things. They go in increments of halves, fourths, eighths, sixteenths, and all of those are mixed numbers that there's different marks between these. There's 12 inches in a foot, and then depending on the tick marks, there may be 16 between each number for 16ths of an inch. There may be eighths for 1/8 of an inch. It just depends. But that's another example of a mixed number. 1.5 inches, 2 and 2.25 inches, 3 5/8, whatever it is. Okay. And then we've talked about, and we'll talk more about reducing fractions. So we don't say 2 and 8/16. Well, 8/16 reduces down to 1/2. So we'd say 2 and 1/2. So that's where the tick marks are usually longer. If it's over 2, if it's over 4, the larger the denominator gets, the smaller the tick mark gets, just to distinguish between 16ths, eighths, fourths, and halves, or the whole numbers, obviously, are the largest tick marks. Okay. And we'll do that practice set when we return, and that's what we have for our new concepts. Hopefully mostly review. If not, You guys can get into MATLAB. We'll have class time to work on these. Bring any questions you have with you, and we will go from there. Thank you.